And today's speaker is Professor Andrzej Nowak, Department of Civil and Environmental Engineering, Auburn University. He will deliver a paper entitled, and that's a hard word for me to say, reliability of structures. I'm very sorry for that. Professor Andrzej Nowak has a very high academic standing both in the United States and globally. Since 2013, he has worked at Auburn University in Alabama, where he has served, among other positions, as Dean in the Department of Civil Engineering. His primary area of research activities is the reliability of building and engineering structures and their limit states of safety, including statistical models of structural loads and capacities, and the verification of these models through testing of natural scale structures, together with Kevin Collins. He is the author of a book entitled Reliability of Structures, which is considered a canon in this field. So, ladies and gentlemen, Professor Andrzej Nowak.
Thank you very much. I understand that I am supposed to speak English, yes? Not Polish, okay. So thank you for the invitation to make this presentation on reliability of structures. And I will start with the important statement. The building structures are expected to be safe. That's what the society expects. And the question is, what is the safety level which should be used? If safety is not sufficient, the structures do not perform well, we can have failures. On the other hand, if safety is too high, then that will result in excessive costs. So to work on reliability of structural systems, we are facing three important questions. The first one is, how do we measure safety? When we talk about safety, can we measure it? Can we know how much is it? And once we know how to measure safety, the next question is, what should be safety? So we call it target reliability. What is the required reliability or optimum reliability? And the third question, once we know how to measure it, once we know what should it be, how do we implement this in practice? How do we make our structures safe enough? And I will start with showing some of the structures which almost last forever. Bridges, which the Romans built 2,000 years ago. 5 of them are in Rome itself. There are other places. These bridges are standing until today. So the time is not necessarily a big factor. This is Pont de Gare. This is not a bridge, it's an aqueduct in southern France built by the Romans 2,000 years ago. And again, the structure is still carrying the load itself, and it's still there. There are structures which are several hundred years old, as this Ponte Vecchio, the bridge in Florence, the beautiful structure which until today is serving without problems. And of course, we have modern structures, which are this one, Golden Gate Bridge in San Francisco. And I especially chose it because at this time, this semester, I am a visiting professor at Stanford University, very close to where this bridge is. So we start with, what are expectations? What the society and what us as users, us as those whom the structures serve, what do we expect? And number one, we expect structures to be performing well. We do not want structures to fail. And that applies to design, that applies to construction, that applies to operation and maintenance. So now let's look at the reality. What is it how the actual structures, how do they perform? We know that some of them, as I showed in some other slides, Roman structures last 2,000 years, no problem. Now, what do we observe? Number one, we see that loads are often much more than what they were in the design. That applies to all kinds of structures, not only buildings, but highway structures and also the space structures too. The loads can be underestimated. The other thing is materials. The capacity to carry the load. Materials can be overestimated. Their strength can be assumed that is more than what it actually is. We have accidents. We have collisions. We have vehicles crushing into the structure. We have other disasters which we have to deal with, such as floods, just the recent floods in Poland, and hurricanes, tornadoes, earthquakes, wind, excessive wind, and snow. You know, all these are, we call them extreme events. And a factor which is really a cause of many, many issues, and that is human error, human behavior, our mistakes, where we misinterpret things and we make wrong assumptions, and that results in a problem. Now, observation indicate that almost all failures are caused by human error. So in a result, the rates of actual failures exceed by far what we theoretically calculate. I will show some of these examples, but I will refer to bridge structures because this is my major area of application of reliability of structure theory. So just to give you an idea, we have over 600,000 bridges, and look, 25% are not adequate. They should not be really opened for normal traffic, and they are not. They have a special signs, posting, maximum weight or so is limited to what is required. 10% do not have load carrying capacity. Just think about it. When you're driving on the highway, you don't realize that the bridge which you are over can have inadequate capacity. That means some of them result in failure. Unfortunately, actual failure collapse is not that frequent, but nevertheless too frequent. And I'll show some examples. This is the situation where a flood caused a major scour problem, major problem with losing the support from under a bridge structure. Corrosion is a major problem, and that is chemical reaction, which can we prevent this? Well, we can, but once it starts, it's going on, and dealing with corrosion is a big issue. As you can see here, the corroded structures. This was a picture I took myself. There was a fishing pier, and look, the corrosion resulting in practically the structural component is gone. We have another cause of problems, and that is collisions. We may have especially construction equipment especially cranes and other structures, the driver may not necessarily know that the equipment is on the way, not all the way down and is going, and that results in the damage, major damage. A repair of this is quite expensive and complicated. We have another example, failures due to construction equipment is quite common. So, so you can see that, of course, the bridge was not designed for something like this. There was a bridge in Minneapolis, and this was about 10 years ago. Bridge built in the 60s, 50s, so maybe 60-year-old. And it's a truss, three-dimensional truss, and they were doing some repairs. And for some repairs, they put some construction materials in one spot. And what happened was, if you look, let me see if my pointer, yes, see this gusset plate, the connection has a steel plate, and it is connecting these components together. This, oh, you don't see it? Okay, well, if I have a pointer, I could, yes, of course I should. This one here, this is a gusset plate. It's a steel plate which connects all these components. This was designed with the thickness, which was half of what it should be, by mistake. And this bridge was already in service for 60 years. There was no real sign of a problem. But when they overloaded this deck, they put material in one spot. It caused excessive stress in that gusset plate. That gusset plate failed, just one gusset plate. Just think about it. The whole structure, big three-dimensional structure, one gusset plate failed and the bridge collapsed. And this was filmed. 15 persons were killed. Major disaster. So, you know, another example, this is a bridge in pedestrian bridge in Miami. There was a university on one side of the highway and the city on the other. And that bridge was designed, pedestrian bridge, as a connector from campus to the city. Everybody was proud of this. This is during construction. During construction, they were still doing some finishing work, and they noticed that there are cracks going on, the cracking of concrete. They wonder what is going on, but they didn't stop anybody from the traffic was going under the bridge. This bridge, because of mistakes of the people in the construction area and the designers, it collapsed, and about 7 or 8 persons got killed. Again, a major disaster. So reality is such that we really have a lot of problems with the structures, much more than we theoretically predict. So now the question is, what are the sources of uncertainties? Where the uncertainties are, what is the cause of it? And I grouped these causes into several groups. I said loads, resistance, which is load carrying capacity, or the other item which I didn't list here are these human behavior, the human error. So the loads, we are all aware, and our intuition tells us that if you talk about wind, it's hard to predict. It's whatever we predict, it's still, there is an uncertainty involved, and the wind exceeds or does not exceed the design values the designer is using. That applies to the other, what I would call natural loads. But then we have the whole group of causes, loads, which are man-made, caused by a human. Collision, we just had pictures of the results of this, and we have vessel collision. If there is a navigational water, a ship or a barge will hit the structure, or we can have a vehicle collision when a vehicle hits the structure. We have quite a lot of causes which are in the category of very rare but dangerous situations, such as explosion, gas explosion or so. On the other hand, this is the load side, load carrying capacity. How much load that a structure may take? Well, that also depends on material properties. It depends on geometry. It depends on the quality of workmanship and so many other factors which are all together combined to provide what we call load carrying capacity. Therefore, we are treating load and resistance as random variables. So treat them, and then we calculate in a mathematical way the probability the structure will not perform its function as required. So what is the definition of failure? Failure, the word failure implies something is collapsing, something is failing. Failure in our sense here is defined as inability of the structure to perform its function. So if the structure performs its function, it's okay. If it does not perform its function, it's wrong. So now you can see, what does it mean, perform function? Depends on what do we have in mind. A structure fails when a beam is broken, when a column is buckling and does not support the load anymore. But failure is also exceeding deflection. Failure is also exceeding lateral sway. If there is a heavy wind and pushes the structure and it just, it's a horizontal load, it tilts to one side, that is a failure if it exceeds a value which we will consider as a critical value. Very important is definition of what we call limit state. The limit state is the condition of the structure which is on the borderline between what is acceptable and what is not acceptable. So if we can define it, is fine, but a definition of that limit state is essential to actually do the calculations. We cannot calculate reliability without a definition of what is acceptable and what is not. And you'd be surprised to know how difficult it is in some cases. Even top experts often cannot agree what is acceptable and what is not. One person's limit is not the other person's limit. Some are obvious, but not all, and that is often leading to very subjective judgments. Mathematical formulation of a limit state, we call it limit state function. And we need to have this describe in mathematical terms what is acceptable and what is not acceptable. So we have various types of limit states. We call some of them strength limit state. That is easy to define. If whatever you have, either a big building structure or a machine or a spacecraft or a submarine or a ship, the strength limit state is defined very similar way. Failure by reaching the capacity of material, by cracking, by breaking, buckling. Service limit state is defined as ability to perform its function. So the structure may be structurally okay, healthy, but it may not have the capacity to provide a structure which doesn't crack. Imagine for food industry, you have a storage area where you store food, and it's a concrete structure. If there are cracks, there could be some bacteria, there could be some other problems. So structurally, the structure may be acceptable, but because of that condition may not be. Fatigue limit state is ability of the structure to take repeated load applications. Very complicated. It's not easy at all to model this because modeling it involves not only limiting the stress value, but also how many times that stress is applied, and especially if the amplitude of the stress is a varying value. Finally, extreme event limit states. As an example, think about a strong earthquake. If there is a very, very powerful earthquake, we may design our structures so that they will partly be damaged, but not collapsing, not killing people. So we define that limit state as our acceptability is more than normal for other structures. We allow some deformation, we allow some excessive deflection, but not collapse. So extreme event limit states are relatively new items introduced in the design specifications. Let me now start with the limit state function. We have a function which is a function of a number of variables. These variables represent load. These variables represent strength. They represent strength of material, geometry, modeling, a variable which represents how good is our theoretical model. And there could be various formulations from mathematical point of view of the limit state. The simplest one is shown at the bottom. Resistance R, takeaway load, the difference between capacity and the load, that is my safety margin. And G is if R and Q are random variables, we treat G as a random variable. Now, the question, what's the probability of failure? That's probability that G is negative. So we already have a mathematical formulation for a simple case. In that simple case, we would consider the different limit state functions for each limit state which is considered. So each limit state has its own, not necessarily the same, but usually different limit state function than other limit states. I listed here some examples: cracking of concrete, also cracking in steel, also the effects of other loads like temperature effect and the loss of pre-stress in structures which use pre-stressing. In general, I could look at this case the following way. The blue density function represents the variation of load carrying capacity. The red one is the load itself, load effect. And the green is the difference between resistance and load, R minus Q. That's the difference, that's my safety margin. And now that safety margin represents my safety reserve. So the probability that safety margin is negative is the probability of failure. The shaded green, this is my probability of failure. In real structures, when we consider probability of collapse, that shaded area is so small that I would not be able to show it here unless you have a very strong magnifying glass. The green area would be within the thickness of the lines which represent the density functions. How do we calculate probability of failure then? Well, probability of failure is calculated, as I said, as probability of the green area taking value, negative value. If the variables, if resistance and load are normally distributed, Gaussian distributions, then safety margin is Gaussian too. And we can calculate this. The formulas are here. I don't want to bore you with the mathematics of it, but this is probability using the cumulative distribution function of normal random variable. We just can calculate this. And if R and Q are normally distributed, G is also normally distributed, probability of failure is very nicely calculated here. Now, there is a special thing which I would like to mention. Probability of failure implies negative word. Failure is negative. It doesn't sound positive. So it was decided several years ago when reliability started to be used in the design. Then we would prefer to, instead of using failure, probability of failure, we were using reliability index term. A reliability index is equal to the standard deviation of the green curve representing density of safety margin divided by the mean value. So if you look at this green density function has the mean value here. This is the mean value. And there is 0 here. The distance between 0 and the mean is in terms of standard deviation. That means how many standard deviations are between 0 and this mean value. That number of standard deviations is called reliability index. And that is very important. And I will talk more about this because especially if there is a legal case and lawyers get things in their hands and they are they are considering a case and they said probability of failure was so and so. It's so much nicer to say reliability index was so and so because they don't understand what is the relationship, and the reliability index sounds positive. So in legal court, it's just better to use that term. So reliability index is equal to the mean value divided by standard deviation. Mean value by standard deviation. And the mean value of G is the difference between mean value of resistance and mean value of load. And the variances are also equal to summation of variances. And this is the very basic. Oh, I'm too fast. Just pressed it and it went too fast. So reliability index is a function of mean and standard deviations of the safety margin. And that is reliability index is so important that Greek letter beta is reserved for it, and it's used in the literature. When you look at reliability index, you will find that it's beta. And it's the formula is very simple. The formula is simple and very accurate if R and Q are normally distributed. If one of them or both are not normally distributed, can still use this formula, but it's approximate. It's not accurate. The problem starts when limit state function is nonlinear, then it has to have special approaches. I will not be talking about the procedures to calculate it because that is, there is a course in reliability of structures where these things are presented. But if you have no other means to do calculations, use the formula which is shown here. Or recently, the way to calculate it more accurately, especially in case of nonlinear limit state function, would be to use Monte Carlo simulations. But I will not be talking about this here because there would be too much. The relationship between probability of failure and reliability index is shown here. So, and again, if you hear probability of failure, that's scary. Yes, well, even if you hear that it's 10 to -4, this is so 1 in 10,000 can fail. But if you hear that reliability index is 3, that sounds positive, and you don't, you are not scared. So now, what do we need to do the calculation? Well, we need limit state function, it's number one, and identify load and resistance factors. We need statistical parameters for load and resistance, and we need reliability analysis procedure. I just showed the simplest case, but the cases can be much more complicated. And finally, we need to have a procedure to calculate how do we implement this? How do we distribute that safety margin so that we produce structure which is at the safety level we want? So I will be using some of the parameters that I wanted to define them. Bias factor, I define it as the ratio of mean value to nominal value. Nominal is what the designer is using. Coefficient of variation is the ratio of standard deviation divided by the mean. Why do we have these? Look, bias factor and coefficient of variation are non-dimensional. It's very convenient because where I don't know dimensions, you can really judge, easily compare one case and the other. Time varying loads, that requires special approach that is much more complicated. And of course, we have procedures for this. I won't be able to talk about this, but we do have the procedures to handle time varying loads. Resistance parameters, we need material test data. We have quite a lot of it, but still there is more data needed, especially for new materials. Quality of workmanship is an issue. How do we assess this? Now, what is the next? So the first question, which I asked the 3 questions, how do we measure reliability? Suppose we already know it. Yes, we have the formula. For the simple case, we can do it. What is the target? What is the required reliability index? Well, if it's too small, it's a problem. If it's too large, it's a problem too. So somewhere in between, too small and too large. And I just consider the major reasons, the major criteria which are used in deciding what is the reliability index as a target. Number 1, consequences of failure. So what happens if your limit state is exceeded? What happens if it's violated? Is it serious? Is it somebody can get killed? Somebody can get hurt? The structure collapse? The structure is buckling? The second most important criterion is the cost. And that is the cost. Look at safety as a commodity. Safety, you can buy safety. Almost like going to a store and buying something. You buy a car, you buy some bread, you buy some meat. And if what you buy is very expensive, you are very cautious and you say, well, we're spending money. You accept something poor quality because it's expensive. The same is with safety. If safety is cheap, we buy more of it. If safety is expensive, we don't buy much, and the society behaves the same way. The society is just like you. Yeah, like when you are a student, you go to buy a car, you buy a junky car and an older car. It's not safe. You know it's not safe, but you buy it because you cannot afford a more expensive car. If you have lots of money, you buy the most expensive car. You don't care about it. That is how the society also looks at deciding what is the target reliability. We have other reasons also, tradition and so on, but these are the first two are the most important ones. Let me show some examples in this consideration. If we design a new structure, the structure is in our computer, and we look at the components and we say, hey, you know, why don't I increase the size of that steel beam? And by this, I will increase reliability index drastically. I will just take a bigger beam. You increase the cost of the structure minimum way, maybe 1%, 2%, very small usually. But now think about an existing structure, and you see that steel beam is not strong enough. What do? Well, if you need to strengthen it, you have to close the structure, bring the team, bring machine, equipment, materials, and so on. That costs a lot of money. So result is we accept lower safety for existing structure than for a newly designed structure. And that's what it is in the society. And I will give you an example for bridges. A steel or reinforced pre-stressed concrete beam in a bridge, newly designed, has target reliability 3.5. For an existing bridge, the target reliability is 2.5, 3.5, 2.5. Why? Because of that cost, because of that economic consideration. The other example I will consider is element versus structural system. If you have a structure, you have a floor in a building, and it has number of beams connected with a concrete slab on top of them. If one of the steel beams is overloaded, nothing really happens. If it's overloaded, the remaining load is taken by other beams, and it's fine. But think about the column in the building. The column, if it collapses, the big part of the building may collapse. So a reliability index of an individual element is very different than reliability index for the whole structure. The failure of a component is not necessarily failure of the structure, and but in some cases it is. So depending on this, there is this difference between element and system reliability. Ductility of materials is important. Are your materials brittle or ductile? And the last item I would like to consider is implementation of the reliability policy. Once we define how do we measure it, and we define what it should be, how do we implement this? Well, there are design codes, there are quality control measures, requirements on qualifications, education. That's why you cannot design a building, you cannot design a bridge if you don't have qualifications. If you do not have a degree from a university, if you don't pass the professional engineer's exam, you cannot do this, because that is the protection. The society protects itself from the possibility creating the situation where there could be failure. So what do? We have better quality of materials. We require materials to be of a certain quality. we predict the loads in a way which is more rigorous and regulated. The quality control is very important to eliminate errors in design and construction. We have a system of preventing failures from occurring by checking system, by control system. And of course, we have adequate safety factor. And that is the thing which I would like to spend a few minutes on. The safety margin is distributed and assigned to those parameters in the design process, which have the, depending how much uncertainty is involved, that is accordingly a safety margin which is applied. And so load and resistance factors are representing our safety margin and are assigned in the formula, in the design formula. And I would like just to show that each load and each resistance have a load factor or resistance factor, which represents the degree of uncertainty, and it represents the adequate safety margin, which is calculated. The calculation is quite complex, but it is done by the committee which develops design codes. For example, if this density function represents a load, then we have average value of the load, average value. We have nominal value of the load, and we have factored load, multiply times factor. And similarly, we have for resistance, very similarly, we have we have the average value, we have nominal value, and we have factored resistance. So the question is, how do we calculate this? There are formulas, and I am only showing you results of the analysis just to show you what factors are involved. This is the factored load for, for loads. It's the mean value plus a reliability index and variance of load and variance of resistance. What I wanted to stress is you cannot calculate optimum load factor without considering resistance also. You cannot calculate resistance factor without including the effect of load. So load and resistance cannot be separated. Each time you do the calculation, it's the three parameters: the load, resistance, and reliability index. Depends how large reliability index you want, you get it different ways. So this is the formula for the factored resistance. Also, you can see the factors which are involved. Both load and resistance parameters are involved in this calculation. In the case I consider, since you are in the Space Center, you may think, hey, how is it related to the structures in the space? They are. I mean, the principles, the formulas which I showed are not different. The reliability is different because the costs are different. If it costs a lot to send a spacecraft, of course, your economic analysis is different, but the principles are the same. So the procedure is not different. The formulation, the need to formulate limit state function is important. There is a need for load models. There is a need for resistance models, but the procedures are not different. And I would like just to show you at the end our new structures lab at Auburn University. This is a new lab, and we are very happy about this. This is the main hall and the student work areas. And this is what we call a strong wall. And it's very busy. We have lots of projects. And if you happen to be in Alabama or in the area, you're welcome to visit. We'll give you a tour of our facility. This is the part of the facility geotechnical chamber. So the conclusions, reliability is a rational measure of structural performance. We still need much more statistical data, and we keep getting it. And the target reliability depends, as I said, on the consequences of exceeding limit state and the cost. So that is it for my presentation. And I understand we still have some time for questions. So thank you very much.
Thank you very much, Professor. And of course, are there any questions? Well, let me just check on YouTube.
We do not hear.
Yes.
And right now?
This is better.
Regarding the calculation of the risk of natural hazard in the construction, obviously they do not have normal distribution. So how do you model it? Because in fact, do you use the probabilities, the vulnerabilities of the zone, or?
Loads, first of all, loads never occur as a single load. They are effect of several load components. So we are dealing with the need to consider load combinations. And load combinations, for combinations of loads, of course, you need statistical data. Most of the cases, statistical data is either not available or is not sufficient. So there is a lot of engineering judgment involved, so subjective judgment involved. There are the model which is typically used for load combinations is so-called Terkstra's rule. And you may consider this, as I mentioned, for space structures, the loads are different, but the idea is the same. And that idea is if you have not correlated load components, then in the combination of loads, only one of them takes extreme value and all the others take average value. It's very simple, but it's very effective and it's very correct. There were many studies which showed that this simple approach is okay. So responding to your question, if you have different load components, we never practically assume that 2 or 3 of them take extreme value in the same time, because it's unrealistic. But if there is a correlation between the loads, it's a different story. Then it's much more difficult. Any other questions?
Thank you very much for your presentation and for being here with us. Thank you.
Okay. There are also no questions from YouTube. So thank you very much, Professor. It was a very interesting lecture, and we hope to see you again at some point. Thank you very much.
Thank you.
You understand English?
So right now you have sound for how does it describe? You are very conscious. Thank you very much. Thank you very much.
Dziękuję panu.